Hello everyone and welcome to Coding Cart. So in our previous session we have solved this problem has path or not in the directed graph with the help of DFS. So this was our code. So this was a recursive approach. So in our today's session we are going to solve the same problem with the help of BFS. So let me do a recap how the things were working in the DFS. So for example I have a graph. Suppose this is a given graph structure. So I have defined the graph with the help of dictionary over here. So for this structure, our graph will look like this. So here we have written a code, recursive approach. So let me explain you here how the things are working. Then we will move forward for the BFS. Okay. Okay, now you can see here. So in this DFS approach, using recursion, you can see here. Here we were passing the graph, source, and the destination. So here our graph and destination were fixed and only source was changing. Suppose for this given graph, suppose our source is 10 and destination is 100. So we have to check whether we are able to reach 100 or not from the source node 10. So suppose we are standing here. So we are passing here graph, source and destination. So currently our source is 10 and destination is 100. Okay. So here we are sending source as 10 and our destination is 100. So for this given graph, suppose we are standing at node 10. So our source will be 10 and destination is 100. So in this graph, here it is checking in this if condition. If source equal to destination is 10 equal to 100. So this is not true. So it will go in this for loop. So if you see here for never in graph for which key source is here 10. So in this graph for key 10 it will return 20. So for in this list, so currently we have only one value 20. So for never in 20, so it will simply give here 20. So this will be now new source. Here we are passing the graph never and the destination. So here never is a thing which is being changed every time. So this will be our new source and we are calling it as path function again. So here it is coming 20. Now again we are checking, is 20 equal to 100? Is 20 equal to 100? Is 20 equal to 100? So again this is not true. So it will go again in the for loop. Now for key of 20 now. So for key of 20, what it will return? For key of 20 it will return 30. So for key of 20 it will return a list which is having value 30. So now in this for loop, for never in, this return value means graph of key 20, which is returning me a value of 30. So for this 20 it is returning a list which is having value only 30. So for if you are using this for loop, it will return me only 30. So again for 30 it is checking. Here we are calling the same function again, the help of recursion. So here it is checking where 30 equal to our destination which is 100. No. So again it will go in the for loop. Now for this 30. So for this 30, now for the key 30, we are using a for loop. For the key 30, it will return a value 50, 60 and 40. Now we are using a for loop. So for the very first time, 50 will be returned. Okay. So again, this 50 is not equal when calling the function. For this 50, it is not equal. So since here we are using recursion, so again it is going to check for this key 50 now. So from here it is going to check for the key 50 now. So for 50 it is having nothing, so it will simply return back, and it will go for the 60. Now 60 again it will check a condition here, 60 equal to 100. So no. So again it will go here for the key 60. So for 60 nothing is present here in the list, so this for loop won't execute since the list is empty. For this 60, it will go for now 40. So for 40 here it will check first whether this 40 equal to 100. No, it is not equal. So for this 40 now, so for this 40 now it will go in the for loop for the neighbor of graph in which we are passing 40. So for this 40 the value will be 100. So for this 100 we are using for loop. So for neighbor in graph of this source. So for the graph of 40 it is returning 100. So when you are using for loop it will simply give a value 100. Now we are passing this as a source in this has path. So here it will come whether 100 equal to 100. Yes, now it is equal, so it will simply return true here. Now here the values are equal, so here it will be returned. Now since this is a recursive call, so all the values will be returned one by one, and at the end we will get the output as a true. So this is how the DFS approach was working. So now in today's session we are going to solve the same problem with the BFS approach. So in BFS we are simply going to use one extra data structure, that is queue. So let me explain with the same graph. Now in this BFS data structure, the logic is very simple and slightly different from the DFS. Here we are going to use one queue. So what we are going to do here is, suppose we have one queue. So we will first put the node on which we are standing in this queue. Suppose we are standing on 10, so we'll put here 10. Now we'll use on while loop to empty this queue. So we are using on while loop to empty this queue. I will write the logic and explain each and everything in detail. So first we are at node 10, so we'll simply pop out this one 10. So 10 is now empty, and we will check whether this value is equal to our destination or not. If it is not equal, then what we are going to do is we are going to simply add its neighbor in this queue. So we are going to add this neighbor, which is 20. Now again we will pop out this. Now again we will pop out this element from the queue. Means our task is to simply empty this queue. So again we will pop out this 120 and check whether this 20 is equal to destination. So currently our suppose source was 10 and destination was 100. So this 20 is again not equal to 100. If it is not equal to 100, so again we are going to add its neighbor in this queue. So its neighbor is 30. So I will add 30. Now again this queue is not empty, so we'll pop out this one. So we will add here 30. So again you can see here 30 is not equal to our destination. So we will add its neighbor. So it's have three nodes, 50, 60 and then 40. So now again we are going to pop out this one. So we will pop out this 50. So 50 is again not equal to our destination node. So now you can see here we have pop out this 50, but 50 don't have any neighbor, so we will leave that one. Now second one is 60. So we'll pop out this 60. So again this 60 is not equal to our destination, and also 60 is not having any neighbors, so we'll simply leave it. Now next is 40. So we'll pop out this 40, pop out this 40 and check whether this 40 is equal to 100. No, it is not equal. Then what we are going to do is we are going to add its neighbor, which is 100, in this queue. Now again this queue is not empty, we'll simply pop out this one. Now this 100 is equal to the destination, means we are okay. So what we are going to do is whenever this pop out element is equal to the destination, we are going to simply return true. Else at the end we are simply going to return false by default. So this is the simple logic using the queue. So let me write the code and let me explain you. So here we are going to write the same logic with the help of BFS, BFS approach, BFS approach, and here we are going to use one queue data structure. So Let me copy this one and paste here. So has path graph, we are given a graph, source and destination, and let us create the graph. Let us create the same graph, this one, in which we are given 10, 20, 10 is connected to 20, 20 is connected to 30, 30 is connected to 30 is connected to 50, 60, and then 40. 40 is connected to 100, and 50 is connected to nothing. 60 is connected to again nothing, empty, and 100 is connected to nothing. So our graph is ready. Now we are going to call this hash path, and here we are going to pass this graph source as 10 and destination as 100. Now here we are going to write the logic. So very first thing is we are going to take one queue. So and here we will pass queue, and here we will pass the source, the very first node on which we are standing. Okay, now our task is to empty this queue. So we'll use on while loop. While this queue is not empty means while queue means till there is a value in queue, it will run. So while queue, so what we are going to do here is we will pop out the element from the queue, and that popped out element will be the current element for us. So current equal to queue dot pop the very first element. So pop up 0. And here we are going to check if this current element is equal to the destination. If it is equal, then what we have to do? We have to simply return true. That's it. Now what we have to do here is, if the current is not equal to the destination, then we have to use the for loop to keep all its neighbor in the queue. So for neighbor in graph of current. So current for neighbor in graph of current means on the node which we are standing, we are going to put all its connected neighbors in the queue. So what we have to do here is we have to keep in the queue. So queue dot append its neighbor, so we are going to use a for loop for the current elements and append all its neighbors. So when all its neighbors are appended in queue, so what is our next task? It will simply execute the while loop till the end, means till the queue is not empty. Till the queue is not empty, we are going to follow the same process since we are doing with the help of iteration. So while queue means if there is a value in queue, what we have to do? We have to pop out the very first element and check if that element is equal to destination. If it is equal, then return true. Otherwise, simply add its neighbor into the queue. If nothing is matching, so by default we are going to return false. Otherwise, if the current and destination are matching, then we are going to return true. So let us run and see. So you can see here it was returning true. At the end we have reached the 100, so it is also returning true. Now let us try for this graph, yesterday's one. So for this one it was returning false, so let me run this one. So now you can see here it is returning false. So it is working. So I hope you have understood the simple logic of the BFS with the help of queue. This was the iterative approach. So if you have understood this one, so you can simply write the logic using a BFS with the help of recursion. Let me give you a hint. Like in the iteration method, we were calling the hash path with the help of graph, source and destination, right? Now the hint is since in the BFS you have seen we were using one queue data structure, so you have to keep the track of the queue. So in this has path method, currently we were passing graph, source and the destination. Now in the BFS you have seen here we were using one queue data structure. So now for your hint you can write a function in which you can pass four things now: your graph, source, destination and the queue, so that you can keep the track of its neighbor. So try to write this recursive approach with your own. So if you are able to write the recursive approach from your end, so do post in the comment section. I will review it from my end. So that's all for this problem has path in the directed graph with the help of BFS using the iteration method. So in our next session, we are going to solve the same problem in undirected graph. So that will be interesting one, and we will also solve the lead code problem. So that's all for today's session. Hope you have understood something new. So if you have learned something new, do like our videos and subscribe to our channel Coding Card and stay tuned for the next video. Thanks for watching.